In this video, we are going to learn how to convert a Volterra's integral equation to an ODE with initial conditions. When you are given a Volterra's integral equation, to convert it to an ODE, first you need to pass the equation through a differential operator. That means you need to differentiate the equation until all the integral signs in the equation disappears. Now the resulting equation becomes an ODE. Now to get our initial conditions, we can get our initial condition from the previous equations. So let's demonstrate it by taking this example. Find the solution of a Volterra's integral equation of the first kind, integral from 0 to s cos s minus t y of t dt equal to s squared divided by 2. And this is the first kind because the unknown function appears only under the integral sign. Integrating from 0 to s, that makes it to be a Volterra's integral equation. Now let's consider this equation. This is our equation. First, we need to pass it through a differential operator. So then now we are going to differentiate each of the terms. So I'm going to have dds integral 0 to s cos s minus t y of t dt, which is equal to the derivative of respect to s squared divided by 2. So you could really see that in our previous video we had something like this, and we apply what is called differentiation under the integral sign. So the same thing to have to apply to this side. So this side I'm going to get del 0 to s, then it becomes a partial derivative here, del the s. Y of s t. So this, after that, you differentiate the upper limit, which is s, and add it to it, d ds bracket x. Then whenever you see t, you replace the t's with the upper limit in this function. The y of s, and you differentiate the lower limit, which is 0. So if you differentiate 0, you still get 0. So minus the lower limit, d ds ds. So this is what you are having, which will be equal to, the of this is equal to, if you differentiate s squared, you are going to get 2s, which is divided by 2. Now if you differentiate this s, you're going to get 1, and the whole of this side 2 is 0. So this equation results in, you're going to get, if you differentiate cos here with respect to s, you're going to get minus sine s. So we're going to have integral of 0 to s minus sine s minus t y of t dt. If you differentiate here with respect to s, this s, we're going to get 1, which what it means what? Plus cos s minus s, this means 0, then y of s. The whole of here is 0, then these two cancel these two, meaning what? S. The whole of here is equal to what? S. So this is the resulting equation. Now we still have our integral equation. Still have our integral inside this equation. Therefore, you need to pass this equation through a differential operator again. Then you differentiate each of the term. We will have dds minus sine s minus t y of t dt plus dds y of s. Then we differentiate this dds s. We still have to apply the same thing, differentiation and then the integral sign. I'm going to have integral from 0 to s del the s minus sine st y of t dt. Then you have to differentiate the upper limit. dds bracket x. Then you replace the t's with the s minus sine s minus x y of x. Then if you differentiate the lower limit and subtract it from it, the lower limit is still 0, so if you differentiate 0, you still get 0, and so there's no need of adding it to it. So plus, if you differentiate y of s, you get what? Y prime of s. If you differentiate this s, you are going to get what? 1. And this side becomes, if I differentiate cos, the sine, if I differentiate sine, I'm going to get cos. So I'm going to have integral from 0 to s minus cos s minus t y of t dt. So if I differentiate this side, I'm going to get 1. So here becomes minus sine s minus s sine 0 y of s plus y prime of s equals to what? 1. Now let's rewrite this as minus integral of 0 to s cos s minus t y of t dt. And sine 0 is still it's the same as 0, so this term is off. Now plus this term, which is y prime of s, which is equal to 1. You can easily see that this equation is same as this equation here. So we now substitute this into this equation. So we are going to have minus s squared divided by 2 plus y prime of s equal to 1. So let's rewrite this nice way. We the same as y prime of s equal to 1 plus s squared divided by 2. So this is an OD. This is a differential equation we are looking for. Now, since it's a differential equation, we need to add initial conditions to it. To get our initial conditions, which is since y prime, we need to get initial conditions of what? Y. So we have to move to our previous equation. In our previous equation, in this equation, you can generate our initial conditions from this side. So since the Volterra's integral equation is starting from 0, so wherever you see s, you replace s by what? 0. So I'm going to get y of what? 0. If you place here 0 to 0, if you integrate from 0 to that means integrating from at a point, that means the whole of here becomes 0. Then here becomes y of 0, which is equal to what? 0, because s is what? Also 0. So this is our initial condition to this ODE. Now, you say you should find a solution So getting this OD with together with its initial condition, you have to solve this OD. We have our y prime of s to be equal to 1 plus s squared divided by 2, and y of 0 is equal to 0. This is the same as what? dy is equal to 1 plus what? S squared divided by 2. This OD is what? Inseparable. So you can use or can easily what? Do this. So let's multiply each term by what? ds. So we're going to have dy to be equal to 1 plus s squared divided by 2 ds. Now let's integrate both sides of the equation. If you integrate this side, we are going to get what? Y. This is the same as y of s, which is equal to, if you integrate this one, you're going to get what? S. Integrate s squared, you're going to get plus s cubed divided by what? 3 times what? 2 plus what? Your constant c. So our y of s becomes s plus s cubed divided by what? 6 plus what? C. So this is the general solution. So to look for our particular solution, you need to insert our what? Initial condition. So if you set your initial condition to this equation, I'm going to have, wherever you see s, you replace it with 0. So I'm going to have y of 0 to be equal to, they will give me 0 plus 0 raised to the power 3 divided by 6 plus c. And y of 0 is the same as what? 0. So it becomes 0, which is equal to 0 plus c. So my c is equal to 0. This implies that my particular solution becomes y of s, which is equal to s plus s cubed divided by 6. So let's consider a different example from this, our last example for this section. On this side, you can easily see that the no function appears under the integral sign, also appears on the other side. So it's a second kind of integral equation. And then the limits of 0 to f, which is a Volterra's integral equation of the second kind. So we have to convert this equation from its Volterra's integral equation to an ODE with initial conditions. First, you have to pass this equation through a differential operator. Now you differentiate term by term. Which is equal to EDS by 2s plus. The differential operator is a linear operator, so you can just bring the 4 outside. EDS go from 0 to s, t minus s, y of t dt. So if we differentiate this side, I'm going to get y prime of s If you differentiate 2s, you're going to get 2 plus, now this where we have to do all the work. Since you have dd's integral sign, now you need to apply what differentiation under the integral sign. So del the s bracket t minus x y of t dt plus the derivative of the upper limit, which is x, d ds. Then whenever you see t in the function, you replace it by this x. So x minus x y of what, x. Then the derivative of the lower limit, which is still 0. If you differentiate 0, we still get to 0. So there's no need of us subtracting it from it. So we're going to have y prime of s to be equal to 2 plus integral from 0, okay, 4. So we're going to have 4 into bracket. If we differentiate here with respect to s, we're going to get minus 1. So here becomes negative integral from 0 to s minus y of t dt. If we differentiate, you're going to get s. You're going to get s minus s is still also the same as 0. So all this term is what, off. So the resulting equation becomes y of s, which is equal to 2 plus 4. Integral from 0 to what? S minus y of t dt. Still, there's an integral equation, there's an integral inside. Therefore, we have to pass it through a differential operator again to eliminate this integral. So differentiate 10 by 10. So for DDS, alright. So if you differentiate y prime of s, it becomes y prime prime s. Y prime prime of s. If you differentiate 2, 2 is a constant, so that case becomes 0 plus. So you need to apply differentiation and the integral sign. So 4 to bracket log from 0 to s del s minus y of t dt plus the derivative of the upper limit, which is s, plus d ds. Then wherever you see t in this function, you will replace it by what? X. So you're going to have into bracket minus y of s. Or if you differentiate the lower limit, is 0, so you are still going to have 0. So all into bracket what? This. Now we are going to get y prime of s, which is equal to 4. If we differentiate this y of t, the function here is a constant, does not depend on what? X. If we differentiate this function, all this side becomes 0. So this makes the whole of this side become 0. That means we've eliminated the what? The integral sign out of this equation. So 0 plus, if we differentiate here this s, we're going to get 1. So plus minus what? S minus y of s So we are going to have our equation to be y prime prime of s to be equal to minus y of what? S. So this the OD differential equation here. I need to what? Find our what? We need to add our what? ODs. We need to add our initial conditions to it. So from the to get our initial conditions, we need to come to this equation first, which is wherever you see s, you replace it with what? 0. So here, if I replace here with 0, I'm going to get my y of 0 to be equal to wherever I see here is 0. So here is of 0. I'm integrating from 0 to 0. So all here becomes 0. Then the whole of this becomes 0. So y of 0 is equal to what? 0. And we come to this equation 2. Wherever you see s, you replace it with what? 0. And I'm going to have y prime of 0 to be equal to. So if I replace it with 0, the whole of this time becomes 0. Now remaining of 2. So y prime of 0 becomes what? Which is equal to what? 2. So the OD, that the initial conditions, y of 0, which is equal to 0. Then y prime of 0, which is equal to 2. And you have to solve this OD together with its initial condition to have a solution to this integral equation. Okay, there is a 4 here, so 4 times this becomes minus 4. So y prime prime of s, which is equal to minus 4 of what? S. Minus 4 y of what? S. So the resulting OD becomes y prime prime of s, which is equal to minus 4 y of s with its initial conditions, y of 0, which is equal to 0, and y prime of 0, which is equal to 2. Can we write this as y prime prime of s plus 4y of what? S, which is equal to 0. So in solving this OD, we know that this function is a solution to this OD. Y of s, let's say 5 y1 of s. Let's say y of s equal to e raised to the power rs is a solution to this integral equation. So we need to what? Differentiate it to get our second term, and replace it and solve this OD. Our first derivative will give us, if we differentiate the top, we are going to get r. So r e raised to the power rs. This is our first derivative. Then our second derivative is going to give us y prime of s, which will, because if we differentiate, we are going to get r times r becomes r squared. So r squared e rs. So we need to substitute this y prime prime then y of s into this equation. We're going to have r squared e raised to the power rs plus e rs. Equal to 0. And you can factorize this the exponential function outside. You can factorize this exponential functions outside, and there's 4 here. Okay, then I have to replace there's a 4 here. Now, if further the exponential function answer, we are going to have ERS to bracket R squared plus 4, which is equal to 0. We know that an exponential function can never be equal to 0. You get it? And so in algebra, we are saying that A dot B equal to 0 is either what A is 0 or B is 0, or both A and B are 0. If this is not equal to 0, that means that this part of the equation is what? 0. So R squared plus 4 should be equal to 0. So if you make, so I'm going to get R squared to be equal to minus 4. So my R is going to now square root of plus or minus 4, which is same as, this will give me a complex number, which is same as plus or minus 2i. If we get an I, can we just replace it into the exponential function and get a solution? But since it is a complex number, we can easily derive that the general solution becomes y of s to be equal to a cos this value here, which is 2. So 2s plus b sine this value here, which is what? 2s. So this is our general solution. Then you have to compete for the particular solution. Where together with this initial condition, you can compete for that particular solution. Now, if having y of 0 to be equal to 0, that means that whenever you see s, you replace it by 0. So I'm going to have y of 0 to be equal to a cos 0 plus b sine 0. Sine 0 is 0. That means that b is of n cos 0 is 1. Then y of 0 2 is 0. That means a is equal to what? 0. That means my a is what? 0. Now what remains is what? Now we need to add this one, compute the next term b. You now compute what? A, which is 0. Now our next term we need to differentiate this function, which is y prime of s, which is equal to, if we differentiate cos, we're going to get minus sine. And if we differentiate this sine s, we're going to get 2. So we're going to get minus 2a sine 2s. If we differentiate this sine, we're going to get cos plus 2b cos 2s. Now we know that our y prime of 0 is equal to 2. So y prime of 0 will be equal to, wherever you see s, you replace it with 0. So minus 2a sine 0 plus 2b cos 0. You know that sine 0 is always what? 0. And cos 0 is what? 1. And y prime of 0 is what? 2. I'm going to have 2 to be equal to 2b. This implies that my b is equal to 1. Now I need to substitute a and b into our general solution. This general solution to get our particular solution. So our particular solution becomes y of s to be equal to our a is 0. So when we place 0 here, this here is off. Now our b is what? 1. So since our b is 1, here becomes sine 2s. So sine 2s becomes the general solution. So this is the solution to the integral equation.